Bismillah ar-Rahman ar-Rahim. Welcome to tutorial 5. And the first problem, it says that investigate the resonance in a series RLC circuit with a system frequency of 50 Hz. XC is given, XL is given, and R is given. So what we like to obtain? We like to obtain what will be the resonance frequency. What will be the total impedance at the resonance, what will be the quality factors. Okay, so let us first of all find the harmonic order. So we can find the harmonic order H by dividing XC over XL. That will give us the harmonic order. We can also find the quality factor, since this is a series resonance, so the quality factor Q will be equal to XR divided by R, and of course XR is equals to HXL or XC over H, or square root of XC times XL. So this is calculated, this is given, then we can find Q. Okay, so H will be 5. Okay, then XR will be 0.3. Then we can find the value of quality factor, XR over R. The quality factor will be 100. Now at resonance, of course, those will be equal to each other, then the total impedance will be only R, and the value of R will be 0.0032. Okay, so at series resonance, the value of the impedance will be very small, or will be minimum. Let us look at this circuit, which is parallel resonance, and again the frequency 50, XC and XL is given, R is given. So again we can calculate H from the square root of XC over XL. We can calculate XR from XL by the square root of XL and XC, and we can calculate the quality factor. In this case, quality factor will be R over XR. Okay, so again H will be 11, then XR will be 5, and Q will be R over X, and that will be 3. Okay, and you will note that the total impedance at resonance will be equal to R, since that value and that value will be the same, right? So those will be the same. As a result, the total impedance will be 16.35. Okay, and look at the impedance. It has maximum value at resonance. Okay, so at 550 Hertz, the impedance will be maximum. Whereas again in the series resonance, it is the other way around. At resonance, the impedance will be minimum. Over here, the impedance will be maximum. Okay. Okay, let us look at this problem over here. So it says that a simple circuit consists of 1000 voltage source supplying pure sinusoidal waveform, and that serve R1 with the value of 1 ohm, R2 with the value of 30 ohm, and at 60 Hertz the value of XL is given 0.49, the value of XC is given as 4.4. Part A, what is for this circuit, what will be the minimum and the maximum impedance seen by the source. Okay, so if we look from this point, what will be the total impedance? The total impedance will be XL parallel with minus JXC parallel with R2 in series with R1, right? So then we can calculate the total impedance as R1 will be in series with the parallel combination of R2 parallel with, so R2 parallel with minus JXC parallel with JXL. That will be the total impedance. Or of course it can be written as 1 over R2 plus 1 over minus JXC plus 1 over omega L. Now if we look at, if we simplify the equation, okay, so this is what we have. So it is 1 over R2 plus 1 over 1 over minus JXC plus 1 over JXL, and then of course we can take a common as J. We're going to end up with this formula over here. So now we can also take XC is equal to omega C, XL is equal to omega L. Okay, so now if the frequency is 0, so 1 over 0 will be infinity, right? This one will be 1 over 0 will be infinity, and then 1 over infinity again will be 0. So at R equal, at frequency 0, the total resistance will be R1. At infinity frequency, 1 over infinity 0, right? But 1 over infinity again will 1 over infinity will be 0. So the total resistance will be again R1. Whereas at resonance that and that will cancel, and then as a result the total will be R1 plus R2. So at resonance the total impedance will be R1 plus R2. Therefore the minimum impedance will be R1, maximum impedance will be R1 plus R2. Okay, this is with regard to the first part. Second part, what is the resonance frequency of the circuit and what will be the harmonic order of the resonance? Okay, of course over here we have XL, we have XC, so we can calculate the harmonic order from XC over XL, so that will give us the harmonic order. Okay, and then we can calculate what will be the resonance frequency. So it will be 60 Hertz times H times the harmonic order. Then plot the impedance. Okay, so anyhow the this one will be the harmonic order 3, and then we can find the resonance frequency. It will be 3 times 60, and that will be 180. Now if we like to plot the relationship between the impedance and the frequency, of course the resonance will be at 180. So at 180 we have maximum impedance, which is 31, because we have parallel resonance in the circuit. Okay, number 4, we have a 3-phase Y-connected transformer with a reactance of 19%. The size of the transformer 80, and it is supplying 50 megavolt load at lagging power factor. Okay, at a low voltage bus of 13.8, 3-phase capacitor is connected, and as a result the overall power factor goes up to 0.95. So we have the initial power factor 0.9, but because we connect capacitor bank, we are able to improve the power factor 0.95. Distribution engineer is asked to investigate the problem, knowing that the short circuit megavolt ampere at the high voltage side is 1600, and he said use a base of 100 megavolt ampere to determine the following. So let me sketch a simple circuit for this one so that everything will be clear. So over here we have a source. Okay, we have over here a transformer, and over here we are feeding a load 50 megavolt ampere, and over here we connect capacitor bank. The voltage over here is 230 kilovolt. The voltage over here is 13.8. Okay, and the XT for transformer, XT 19%, 0.19, and S for the transformer equals to 80. Okay, so this is the simplified circuit, and we have again S load is 50 mega, and the power factor is 0.9. Okay, now once we connect capacitor bank, the power factor improved to 0.95. Okay, so this is the simplified circuit, and he said that use the base of 100 megavolt ampere. Part 1, calculate the current base for the high and for the low voltage side. So we need to calculate the base current. So the base current, we know that the high base for the low voltage is equal to S base, which is 1000 divided by root 3 V line. On the low voltage we have 13.8. Okay, so this is 1000, and then for the high voltage, instead of 13.8 we're gonna have 230. Okay, the impedance base for the high and for the low voltage. Okay, so if we like to calculate now the S base, so Z base, so Z base for the low voltage side will be equal to V low voltage side square, which is 13.8, divided by S base divided by 100. So that will be the base impedance for the low voltage side. For the high voltage side will be 230 divided by 100. Okay, so that will give us the base impedance, the transformer impedance in per unit, and then of course the transformer impedance is given as 0.19. This is of course on that base, on 80 megavolt ampere base. But now we like to calculate the per unit for transformer on the new base, on the 100 megavolt ampere base. So we know that X new will be X transformer per unit. So this is the new, this is old, and then we're gonna multiply it by by S old divided by S new. S old divided by S new. And then you will find the result. Of course, for part C, if we just check. Okay, so you have the old impedance multiplied by the new base over the old base, and that will give you that value. Of course, I mean, to find the impedance in ohm refer to the low voltage side, you multiply it by the base for the low voltage. To find the impedance refer to the high voltage side, you multiply it by the base for the high voltage side. Okay, the short circuit reactance of the power system at 230 bus in per unit and in ohm. Of course, to find the X over here, well, we know that X for the source in per unit will be equal to 1 over S short circuit in per unit, and S short circuit is given 1600, so we can find this one 1600 divided by S base, 1600 divided by S base over 100, so that will be 16. So then XS per unit will be 1 over 16. Okay, find it in ohm, refer to the at 230, so we need to multiply it by Z base for the high voltage side, and then you do it for the low voltage side. Okay. Okay, so the X short circuit in per unit 1 over 16. Okay, we did that one. And now if we like to find the value in ohm. Okay, so what we need to do, we need to multiply the per unit by, so we need to multiply the per unit by Z base. So per unit, which we have already calculated, divided by Z base low, that will give us X short circuit referred to the high voltage, to the low voltage, and if we multiply it by the high voltage, that will give us X short circuit on the high voltage side. Okay, next one. He said, what is the next question? Okay, we found that one. The rated power of the load at lagging power factor in per unit and in megawatt. So we know S is equal to 50, then P is equal to S cosine. So S times power factor, that will give us the power in megawatt. Divide that one by the base, that will be in per unit. Calculate the size of the capacitor bank needed to correct the power factor 0.9. Okay. Yeah, okay, so this one I think we did several problems. So we know that the Q for the capacitor will be equal to Q will be P tan theta 1 minus tan theta 2 theta 1 cosine inverse of 0.9, theta 2 cosine inverse of 0.95, P. We have P, which is 50 times 0.9, so that will give us Q, and then we can find the capacitor, the reactance of the capacitor, by saying that it will be V squared divided by Q, where V is 13.8. Okay, which is given over here. Okay, 13.8 divided by Q. And that will give us the value of the XC. Then we can find C, of course, straightforward. So to find the harmonic order, course, we have a transformer and the source impedance collected in series, so XC over X, the source impedance and the transformer impedance. If we like to find what will be the capacitance, what will be what will be the reactance of the capacitance in ohm, if we convert the Y to delta. Of course, we know that if we convert Y to delta, then that means each side of delta will be equal to 3 times one side of Y. So 3 times, okay, 3 times XC for Y 27, so 3 times 27, that will be 82. Then we can find the value of the capacitance.